So today we're going to take a look at the 555 timer. This is an IC commonly used as a timer or oscillator as well as a single shot trigger. So the way this thing works is it has two modes, and the first mode is called astable mode, where it will just oscillate back and forth between high and low the whole time that it's running. You can change how long the high period is going to be and how long the low period is going to be. The second mode is called monostable mode, where it stays low until a trigger event happens, which causes it to go high for a set amount of time and then go low again until the next trigger. So here's a circuit diagram of what we have on our solderless breadboard right now. And this is actually packaged in an 8-pin dip. And on 8-pin dips, pin 1 is usually up here in the corner. And you can't really see it on the camera, but there's actually a little tiny dot on the package of the IC right about here. So pin 1 is ground. Pin 2 is our trigger input, which we're actually wiring into the back of our circuit to get it to trigger over and over. We have an output pin that in our case is wired up to this little green LED you see blinking on and off. We also have a knotted reset line, so we have to tie this to 5 volts or whatever VCC is to keep the chip from going into reset mode. We also have a control pin that is usually just wired up to a small filter capacitor, so in this case 0.01 microfarads. That's the kind of information you get out of the datasheet. We also have a threshold pin, which is what the timer uses to determine whether it should trigger and go into one mode, the high mode, or back into the default low mode. The trigger voltages on the 555 are actually 2/3 VCC to go into discharging mode and 1/3 VCC to go back into charging mode. And we'll see more about that in a second. We also have a discharge pin. Whenever it's in discharge mode, it grounds this pin. And finally, we actually have a power supply that we're hooking up to 5 volts. So we have this hooked up in monostable mode. So when everything starts up, our capacitor is discharged, and we have these 2 resistors here that are going to start charging it toward 5 volts. And so it starts charging, and once it goes over 2/3 VCC, that's a high enough voltage to go all the way over and hit this trigger line and get it to switch into discharge mode. And at that point, the output goes high, the discharge pin gets grounded, and we start discharging just through RB. And so since this is going to be less resistance, we're going to discharge quicker than when we charged through RB and RA. And then once we're discharged down to 1/3 VCC, this threshold pin sees that again, and we reset back into charging mode. And if you really want to know the formula for the charge time and discharge time is about 0.7 times RA plus RB, all multiplied by C. And that might seem like it's going to be a really long time because you might have some really big resistors, but remember the capacitor is in, the units here are in farads, and since usually we work with microfarad or nanofarad capacitors, this actually can be a very short time. And then the discharge time is very similar, only now it's 0.7 or so times just RB. Again, multiplied by C. So we've hooked this up with a pair of matched capacitors, and in this case, I think we have a 10 microfarad. I could be wrong, capacitor, and sure enough you can see it over here blinking away. So what we're going to do next is we're going to hook this up to an oscilloscope so you can actually see what's going on. Before we get started, I'm going to go ahead and hook up a shared signal ground between the oscilloscope and our circuit so that our measurements actually make sense. And I'm going to hook up channel 1, which is the yellow on the screen, to our output here, which is going to our LED. And so it's going to just tell us the same thing as our LED, going high and low. But it's pretty easy to see that we're actually staying high twice as long as we are low. And this is because RA and RB are the same value. And when we go to charge up, we're charging up through both of them with twice the resistance. So it takes twice as long to charge up. And that's the high part here. And then when we go to discharge, we just charge just through RB. So it takes half as long with half the resistance. But the other thing I wanted to show you here is the voltage that's actually coming out on this net right here connected to the positive side of this capacitor. And so we can actually hook it up and hopefully see, there we go. We can watch it discharging and charging that capacitor up and down. The other thing to note is that if we swap this out for a different capacitor, we'll get something a bit quicker. So I'm going to pull the old one out, and you notice that when I have that other capacitor pulled out, it's actually just freaking out right now. And so let's put this much smaller capacitor in. This one I believe is a 0.1 microfarad. And you can see what looks just like noise. But that's because we're going way too slow. So if we crank our oscilloscope way up, we actually start to see the exact same thing we had before. Only now it looks like our frequency looks like 154 kilohertz. I'm sorry, 154 hertz. So this is actually blinking just a little bit too fast for the eye to see, and probably won't show up on the camera. You'll just see it on, it looks like it's on halfway. So there you go. That's the 555 timer running in astable mode. And if you wanted it to be monostable and use it as a single pulse, you just disconnect that trigger and reconnect it however you want. There's also many other uses for it, because these don't actually have to be fixed resistors, and this doesn't have to be a fixed capacitor. But for all those kinds of things, you'll have to check online.